Good afternoon, everybody. My name is Dhruv Iyer, and I'm a sophomore from Hamilton High School in Chandler, Arizona. Every day, we take many things for granted. We interact with family members and friends, drive to work or school, and use the computer. However, for a large number of Americans, these simple tasks become nearly impossible. The 2010 U.S. Census revealed that over 250,000 people are living with quadriplegia. Because of disability, these people can often feel socially isolated. However, computer games provide us with a fun way to interact and make friends. So if a technology was developed which worked with the limitations of a quadriplegic and allowed them to use the computer, then we may start to tackle this issue of social isolation. And this was the motivation for my project. So today I'm going to walk you through the problem I set out to solve, then I'll walk you through my solution, and then lastly we'll evaluate that solution to see how well it'll work to solve this problem. So once again, my problem statement is that quadriplegics cannot use their arms and hence cannot use the computer to play games. So my goal is to build a device which can execute keyboard and mouse commands to allow them to do that. So the first step was to evaluate the design constraints and success criteria. So I began by looking at the user demographic and found that C1 quadriplegics can only use their muscles above their neck. Then I looked at the game applications and found that there are two types of games: point-of-view games and single-point input games. Point-of-view games would be Call of Duty, and single-point input games being Angry Birds. Once I looked at these two games, I was able to extrapolate a set of the keyboard and mouse success criteria. So then the next step was to look at existing solutions in the market. So devices in the market today aimed at helping quadriplegics use the computer are not an adequate solution. They cost well over $1,000, which is not affordable by this demographic. Also, they do not have the functionality required to play computer games. So then last year I attempted to prototype some wearable devices to solve this same problem. However, these devices, although exhibiting high accuracy and reliability, they were not usable by this demographic. They have relied on head movements, which C1 quadriplegics cannot do. So then this year I resolved to build a natural user interface, a device which doesn't have to be worn by the user, which would track facial movements and eyeball movements in an effort to give keyboard and mouse commands. So let's start with the face tracking development here. With the sensor that I used was created by Microsoft. It's called the Kinect V2 sensor. That's this sensor here, and it was developed as part of the Xbox series, if you're familiar with that line of consoles. And so that's the sensor that I used in this device. One of the questions I'm asked a lot is, how does the Kinect fit into the rest of the project? And I say that the Kinect is providing me with advanced vision processing algorithms. It gives it's a modification of the general vision processing algorithms that you can find in the computer science world. It also includes a high definition camera as well as an advanced depth sensor. So I equate it to being given an engine and asked to design a car. So there's a lot of extra work that has to go into building an application, and that's my job as a developer. So let's take a look at how I did some of this. So if we look at the face tracking device, you see I have three development tasks which I had to accomplish. First, I had to decide on which facial data I wanted to collect. I decided to collect the Canti 3 wireframe model animation units, which you can see right here. And these are just general actions which we can accomplish every day. Then they have to process the facial data, I wanted to go with a neural network. And then to send the commands to the game, I went with a GlovePy sketch to actually send the commands. So the overall program flow starts with the user inputting a facial action into the main WPF, which is the main interface for interacting with the device. Then that data is sent, the facial data is sent through a neural network which determines the user intent. Then it's sent, the chosen command is sent through the GlovePy sketch into the game. There's a three-step process for using the device for a new user. First, they must discover the usable animation units that they can use to power the device. Then they have to select and train the commands that can operate as inputs into the neural network. And then lastly, they are able to use the device to its full functionality. So let's talk a little about those three steps. These three steps I had to specially formulate for this device so that people with different facial structures can use the device. So the first step is to eliminate animation units which the user cannot accomplish. Then after that rough cut, then there's a finer cut where I look at what the Kinect reads when the animation unit is executed versus when it's just a neutral face. So I'm looking for a high difference between these yellow and blue values, which will be good indicators of how well the Kinect can recognize that action. Once I finish these two steps, I'm left with a series of accessible animation units, which I can then combine to form actions. The user then takes these actions and trains the neural network on them. and this allows them to use the device. So this is the neural network, and it's programmed in MATLAB. It is a pattern recognition neural network with 3 layers. It takes in the 18 animation units and outputs the 9 commands that we can execute through the interface. And here you can see how that is integrated into the rest of the program. So for eye track, so now that was face tracking, let's transition into the eye tracking mouse, which is a similar relationship how the Kinect provides the raw functionality. Well, the eye tracking device, the eye tracker, provides that eye data for me, and it tells me where the user is looking on the screen. So as a developer, I constructed 2 different applications depending on the point of view game versus the single point input game. So for point of view games, I divide up the screen into 9 regions. Depending on where the user is looking, that's the direction that the mouse will move. For pointed select games, I simply set the user's gaze set the mouse directly to where the user is looking. However, this is most susceptible to 2 types of error. Eye tracking error in the device, as well as involuntary movement of the eye. So here is a quick demo video just showing how how all this stuff integrates together. You can see I'm playing a game called Portal 2, and I'm moving my face and able to move the character around, and also I'm able to look around the scene. So for the test setup, I had to test each device in accuracy and speed. So for the keyboard accuracy, I simply compared the ratio of correctly sensed versus incorrectly sensed commands. For keyboard speed, I wanted a practical approach. So I had the user actually play the game using the device. For mouse accuracy, I wanted to see how fine of a control I had with the device. So then I had the user click these points and try to get as close to the center as possible. For mouse speed testing, I again went for the practical approach, putting the user inside of a 360-degree sphere where they have to look at different targets. So now this is the data, and I tested the device on 4 different people with varying genders and facial structures, as well as ages. So I wanted to really isolate whether facial structure, age, gender has an effect on how well the device can recognize their face. And I concluded that it doesn't. You can see regardless of the facial structure, this device still exhibits remarkable accuracy. However, there are limitations to this data. You may notice that in some of these blocks there is no data. And the reason is because that command was not recognized at all by the interface. Now, as a practical matter, I would not use that command. I'd have to go back and have the user retrain the interface on a different command because that is not being recognized by their face. You can, the discovery data, which you can see right here, this matrix, is actually a good indication of what you'll see in the accuracy data in cases when we have high ranges, like for example the 0.71 difference. By the way, these are on scales of 0 to 1. So the 0.71 difference between the jaw open means that the command ID 1 will work very well. Also with the eye tracking, speed, accuracy, and the keyboard speed, all 3 of those were acceptable for gaming and fit within the design success criteria. Some conclusions we can draw. First, technology relying on muscles above the neck, or technology for quadriplegics must rely on muscles above the neck. Second, we can distill games down into point-of-view games and single-point input games. We can also look at how current devices on the market are not meeting this cost, functionality, and usability criteria of this demographic. And so I built a successful keyboard emulator which uses face tracking, and it fit within the design criteria and was usable for gaming. And similarly for the mouse, I built a successful eye tracking mouse which was able to be used by these people for gaming. So a neural network allowed me to recognize different variations of the same facial gesture. And as far as the cost goes for this device, my goal is to keep the code open source because that way the cost stays low. The only cost from this device would be about $300 for both of the sensors, which is a major improvement over what the $1,000 users currently have to spend. So some implications, we can distill everyday actions into either requiring one input or more than one input at the same time. This device, at its core, converts facial gestures and eyeball movements into commands. So any action which requires more than one command at any given time can be done theoretically through this device. We're talking about expanding this device into not just playing with games. We can also use the computer, like surfing the internet, as well as driving a car. However, gaming provides a safe way to test the interface before I crash my Honda Odyssey. So the user demographic is not just limited to quadriplegics. I know I mentioned them a lot in this presentation. However, this device is able to be used by people who have use of their facial muscles and eyeball movements. So this device could potentially be used by amputees and people with ALS as well. So some expansions. First, adding more commands into the device. to increase that functionality, adding more customization options to increase the usability, and as well as we can add implement some sort of next command prediction or next word prediction to speed up gameplay or typing. So these are my references, and I'd like to highlight two people in particular. Eric Henning, who I work with at the Arizona Spinal Cord Injury Association. We only met twice to discuss this device, and I just presented the device to him, and he gave a review on it, and his feedback was very essential to making sure that the device was usable by quadriplegics. Eric is himself a paraplegic, but he works closely with quadriplegics. Another person is Dr. Sunil Jain, who I work with at the Scottsdale Rehabilitation Center. He also works closely with quadriplegics as a rehabilitative specialist, and he provided me with similar advice. Again, I only had 2 meetings with him, but it was enough to say that the device would work. So, in summary, the first step I took was to recognize a widespread problem that's affecting many people, and it has an inadequate solution. These devices cost too much money, and they don't have the functionality needed. Second, I was able to brainstorm several alternatives to the solution, prototyping wearable devices, which I did last year, versus prototyping a natural user interface, which I did this year. And then I built a successful face tracking keyboard and an eye tracking mouse, and I was able to test these under the conditions of use by testing it on 4 different people with different facial structures. And then lastly, I was able to determine some ways to expand the device as well as potential uses for the device currently. So with that, I'd like to conclude and open the floor to questions.
Questions from the judges, please?
Can you explain a little bit more about how you went from the sensing the facial device to getting it into whatever the game, so it thinks it's a keyboard command versus coming from somewhere else? How did you sort of circuit that into it?
Yeah, so let's go ahead and go back to the general program flow. So this is really an interaction between many different programs all having to work together in order to accomplish this task of sending a command. So the C# code, when it receives at every frame, it's going to receive an image, and then it's going to go through this process of finding a skeleton and image. This process is sped up if there's already a skeleton being tracked. But once that's the case, then the Kinect can report back with a matrix of facial data, and then it will, from that, extrapolate what the values of these animation units are. So I have these values of these 18 animation units, and I send them as a single array into the neural network. And so the neural network has a system of weights and balances, which it then feeds all of this data through, and then from that it outputs which of these 9 commands, which of the 9 commands that you saw, which is the most effective, highest likely the one that's being selected. And so then that data is reported back to the main code, and then it can execute that through the GlovePy sketch. The reason I went with that GlovePy sketch instead of C# has libraries that robotically press keyboard commands, I have to go with the GlovePy sketch because the games I was using required a special protocol, which the GlovePy sketch was the only one that seemed to be able to execute that.
And then coding for that MATLAB, is that done by yourself? Or?
Yes, that's my coding. The reason I used MATLAB also, I think it was probably over here, was that MATLAB I had several options. I could go with Java, C# or MATLAB, but MATLAB was the best documented, and it offered the best tools to actually develop the neural network and edit it very fast, rather than create a huge code. Yes?
Okay, you talked about, I saw your video and you had the timing, you had reported some of the timing. How much did the latency issue fall into this? Like, did you consider that?
I did. So in the video, I have that screen capture running, so that's why it seems very slow.
Yeah.
And so that was a big issue when I was doing the screen capture. But otherwise, using the device, you can see from this keyboard speed data that the device was still running very fast, and it was usable for gaming. So there's not that much latency in the device.
Well, I'm just sorry, like a comment you said. I know you wanted to keep that to be open source. Have you considered using R instead of MATLAB?
I have not.
Well, I'm just throwing it out there.
Okay, yeah.
It's easy. If you know MATLAB, you should be okay.
Okay. Yes.
This is great work. This is a good solution to a very important problem. The question I have is, I'm trying to understand what you did personally as far as hardware is concerned in connecting, hooking up the Microsoft Connect to measure those facial gestures and to get it into the computer, or was your work more on the software coding algorithm side?
That's an excellent question. My work was done in the software side. The reason is because I could have gone with a system where I used, say, a webcam, or I built my own camera, but in that case, the device hasn't been rigorously tested and it's not an optimal device. So it's easy to hook up the Kinect and get it to work.
So just so you hack, reverse engineer.
Yeah, I hacked it.
Gotcha. Thank you.
Yeah, so just to follow up on the software side. So part of the issue is making a rapid and accurate response to what the user wants in the game. Like, in the game, it's okay if you make a mistake, but in the car, it's much harder, right?
Yes.
So how did you select the machine learning? I guess you suggested like a neural network. So why did you do that? And can you explain a little bit about that?
Right. So let's talk about two aspects of the machine learning. The size of the dimensions of the neural network, as well as why a neural network at all. So why a neural network? It's very interesting, kind of a strange way of solving the problem, but the neural network allows for the recognition of different variations of the same facial gesture. Another option is to hard code the values for every single animation and for every single command. However, in that case, if you don't replicate a command exactly, the device will fail. Also, multiple animation units are being activated when you do a single command. Neural networks are very good at solving problems like that. Now, for the size of the neural network was very interesting. I had to read a couple of papers on how to pick the size. One paper suggested that for pattern recognition neural networks, I only needed one hidden layer, so I went with that. And then for the size of the neural network, I started out with a very small amount of neurons, and then I added more neurons. I added more neurons onto that. I actually had to edit that neuron count as the accuracy went up and down. And you can see, because I was looking one at this axis to see how low it can be to get a very small error, as well as making sure that the testing and the validation for the neural network those curves are followed very closely, so I know the neural network will work well. Does that answer your question?
Time for one more question. Judges? I have one. You had at the beginning, you were talking about sound and voice, yet there was nothing in here to complement the facial stuff with voice. Was that a conscious decision, or why was that not?
Oh, yes. So why did I not go with the voice recognition? That's a very good question as well. I had several different options for this natural user interface. But voice recognition is a very tricky thing to work with, because in a game, you're pressing and holding the keys down. But in voice recognition, especially if you go with the command like forward, well, how forward do you go? So one way in which we can do voice recognition is if we develop a system in which recognizes the tone, like singing. That would be a case, but you can't do repeated actions with voice recognition. So that's why I decided to go with the face tracking and eye tracking as opposed to voice.
Let's thank our presenter once